So we're about to begin the most important ideas of the entire year, and that is Newton's laws and how to use them. Isaac Newton, brilliant guy. He and Einstein are considered the greatest physicists of all time. It's kind of not a fair thing to compare. There have been a lot of incredible human beings over the years, but when it comes to the impact that their ideas had on society and on our understanding of the universe, I don't think anybody compares to Newton. Before Newton, there was craftsmanship. After Newton, there was engineering. Before Newton, the universe didn't make any sense. It was very mystical. It just was what it was, and we just kind of went along. After Newton, we started figuring out that the universe made sense, and that we could figure it all out. He's one of the now he did his work. A lot of his work was based on the work done by Johannes Kepler and Galileo and others, but he took their work and brought it to another level. So, and here's what's really kind of cool. He wasn't very old when he did this. He was a young man going to college, and there was a plague sweeping through London or through England. And by the way, London was a place where they constantly had to have people moving to the city because people died so rapidly in the cities. They were disgusting places to live. Imagine a city of almost 1 million people. Okay, and London, I think, was one of the biggest cities in the world at the time. But there's no real sewage system. There's no real garbage pickup. So sewage, garbage, just kind of thrown out into the river, into the street, rats everywhere, flies, cockroaches. It's just horrible. And people lived in it. They lived in their own filth. And the plague, of course, is caused by bacteria. It's carried by a flea that's carried by rats. So the city was full of rats. And so when a plague would go through, people of means, if you had the money, you got out, because they did discover that if you weren't in the city, you tended to have a higher survival rate than if you stayed there. So he went out to his family farm. And he had nothing to do. He didn't like manual labor, so he didn't want to go out there and work in the orchards or anything. So he decided to sit in his room and over a 2-year period invent physics and calculus all by himself. He was kind of a loner. He was really not a very nice man. He wasn't exactly a socialite. He considered it one of his greatest achievements was to die a virgin. So I don't know what that means, but I will say this: he's one of the greatest human beings who's ever lived. In terms of what he did, it is absolutely no coincidence at all that the Industrial Revolution began soon after Newton published his ideas. And so we owe our modern world to Isaac Newton. Now, actually, somebody was going to figure this stuff out, I think, eventually, but it may have taken another 100 years. Or, so we might be 100 years behind where we are today. So he's a really interesting guy. There's some good biographies of Newton, and he did get really mystical later in life. He wanted to transform lead into gold. He became an alchemist. He really got into, I forget what it's called, but where you search for patterns in the Bible to make predictions and that sort of thing. So he got pretty mystical later on, but the work he did for calculus and physics is just wonderful stuff. And actually, and by the way, by today's standards, we're going to go through this, and you're going to think, why was this such a big deal? It kind of makes sense. Why did it? Well, remember, population was relatively small. The vast majority of people lived in poverty on farms. They were peasants. Only a tiny fraction of the population was educated. And so somebody had to be first to do this, and it was him. Also like Newton, because we won championships out of the Newton's field. So, it was destiny. All right. So let's talk about his first law. We have 3 laws. We call it the first law the law of inertia. Then the second law, a law of acceleration, which is expressed by this equation, F equals ma, the most important equation in physics, in life. Okay? We'll talk about gravitational force and so on. Then we'll talk about the third law, law of interaction, and then from that we'll come up with a discussion of free body diagrams. So let's begin. So if I have an object at rest, let's say, let's put an apple on the ground. Apples are kind of hard to draw, so you can just draw a ball or something. Here's an apple. And it's just sitting there. Really, this apple is just going to continue to sit there until what happens? Yeah, until somebody comes along and forces it to change what it's doing. Now, someone could take the tabletop away. Maybe if sitting on a table, you can remove the table really fast and the apple will fall. Due to gravity, right? Because gravity's pulling on it. Or someone can pick the apple up to eat it or kick the apple. But something has to happen. Some kind of outside agent has to work on this apple, has to do something to this apple to change its motion. Now, people weren't stupid. They knew that. They knew, hey, something's going to, if I have a remote control, that remote isn't going to change what it's doing unless I force it to change. But here's something that is unusual that they didn't really understand. And Galileo is really the first person to figure this out. What if I took this apple and I carved it into a perfectly round ball and gave it a nudge and it started rolling? And it started rolling in this, off to the right. Well, what's this ball going to do? If I roll a ball on the floor, what's eventually going to happen to the ball? It's going to stop. It's going to hit stuff. It's going to roll. It's going to roll to a stop. So people believed before Galileo and Newton, people believed that the natural state of objects was to be at rest. Everything wants to be at rest. In fact, that was why people believed that the earth had to be the center of the universe, because the earth had to be at rest. How could the earth move around the sun? It'll eventually stop, and so they believed that things would always come to a stop. But Galileo figured out, no, actually what's happening is that objects are being forced to stop. You have wind resistance. You have a little bit of rolling resistance. Maybe it'll run into something. It's giving off sound. So if you remove all of that, if you take this ball and just put it into outer space, and there's no atmosphere, and there's nobody to stop it, no gravity nearby, nothing, and you threw this ball will continue to move with a constant velocity. That means a constant speed and a constant direction forever. Forever. So the first law basically says the law of inertia, and we say objects have inertia. Now that's really another way of saying objects have mass, but what it really means is this: the law that an object doesn't change the way it's moving unless forced to change by an outside agent. Now there's lots of ways of expressing the first law. You read it in books. This is the way I like to think about it. Some outside agent has to force it to stop moving the way it's moving. Or some outside agent has to get it started. But if you want to change its motion, something has to push on it. Something has to pull on it. Okay, something has to act on it. Otherwise it won't change. So that's the law of inertia. And it seems kind of obvious to us, but you live in a time where floating in space is something that you've seen on television and you can imagine very easily. That was an impossible concept to people. And in fact, even Galileo didn't imagine something floating in space. What he imagined was a plane that was perfectly flat with no friction and a ball rolling on a plane. And that it would never stop. It would never stop. If you took away the air resistance and friction, it would never stop. Newton extended that to all objects moving in any direction. So that's the first law. Okay, let's talk about the second law. And that's the law of acceleration. Okay, and where did I put it? I can use this. Doesn't have batteries in it, but so here we have a little car, and if this car is going to accelerate, something has to push on it. Okay. Now, really, this is kind of a restatement of the first law and the second law are very closely related ideas. That an object, we want to change its motion. We want to accelerate an object. Now, in the last unit, we described motion very carefully and precisely.
When is your prep period?
Fourth period.
Fourth period?
Yeah, I'm recording a lecture right now, so.
All right, sorry.
Real quick, what do you need?
Remind 101 commercial. I was going to ask you about it.
Okay, yeah,
All right.
fourth period. That'd be fine. So if you have a car of some kind and you want to accelerate, well, there's, you can have an engine in it and you can spin this wheel and you can have a friction and it can interact with the ground, or you can have somebody get outside and push on the car, and or you could have a rocket engine that blows stuff up and throws it out the back end, causing this thing to move the other way. But you need a force to cause an acceleration. Now, in kinematics, we described motion, we described acceleration very carefully, but we never talked about what causes an object to accelerate. And it turns out that we have this interaction with the outside world will cause it. And we call it something that forces something to change its motion, we call a force. So we call something that can change the motion of an object a force. Force. An interaction between objects that can change their motion. Doesn't mean it will change their motion. You can have two forces interacting in such a way that they cancel each other out. Like if this car is at rest on this plane, you have gravity pulling it down, but you have the ground pushing up on it. And so those two forces are going to cancel out, and there won't be any acceleration. The object will be in what we call equilibrium. And we abbreviate force with the letter F. So we can say this is force. And then we use subscripts to describe the force. Maybe this is a pushing force or an applied force. So I'll call this F sub A for applied force. We have lots of different forces with lots of different subscripts, and you're going to get used to that. You have a force of a rope pulling. We'll call that a tension force. Somebody pushing, sometimes called a contact force. We have the ground pushing up on that. We call it a normal force. We have gravity pulling things down. We call that the gravitational force. And then we have the interaction between two surfaces that's parallel to those surfaces, and we call that friction force. And then later on, we're going to have electromagnetic forces and nuclear forces, and there's all kinds of different forces in the universe that we're going to deal with. And so we all F sub something, and that something will tell you what kind of force we're dealing with. But if this is the only, if this is the force and there's no friction or anything on it, we know this car will accelerate. But how much acceleration will you get? And it turns out, and this is an empirical law of nature. And by the way, notice that, how did I draw a force? I made it an arrow, right? So what does that mean about forces? Forces are vector quantities, right? So you put a vector hat on it. Forces are vectors. Now, it turns out that the acceleration of the object will be in the same direction as the force that I'm applying here. So this force will cause an acceleration. And it turns out that the amount of acceleration you get depends on how much stuff you're trying to push against, right? And this is total common sense. If some object has a whole lot of stuff, it's hard to move. It resists acceleration. It has inertia. Okay? And so, and we call that that inertia, that amount of stuff, we call it mass. Now, mass in chemistry is quite often defined to be, the sum of all the material in the object. You add up all the protons, neutrons, and electrons, and so on. In physics, we have a slightly different way of looking at mass. We look at mass, it's almost like we define mass this way. Mass is the ratio of force over acceleration. So if I take an object and I apply a force to it, and I measure that force, and I measure the acceleration, I can figure out how much mass I have. This is what the astronauts do on the space station. How are you going to weigh yourself on the space station when there's no, you're in free fall, right? So you can't stand on a bathroom scale. Well, here's how they do it. They sit in a chair on a spring, and they pluck it. And the astronaut swings back and forth. And so you need a force to stop the astronaut and then bring him back the other way, and to stop them and bring back the other way and the other way. And they measure those forces and those accelerations, and they calculate their mass. Now, it turns out we don't really define mass this way. We could have. We could have defined mass this way. But we do actually define mass based on how much stuff there is. There's this slug of platinum in France somewhere, in Paris probably, and it's in this sealed chamber, and the amount of stuff in that little ingot of platinum is by definition 1 kilogram. I think they still use that as the definition of a kilogram. So we have a kilogram. Oh, and Patrick, can you go get me a kilogram? It's in the 908 in the cabinet just to the left of the door on the bottom. You'll find it. So we have a kilogram mass. So mass is defined to be in kilograms, which is kg, abbreviated with kg. And here's a kilogram of mass. Now, and so if I want to accelerate this, okay, I've got to apply a force to it, and the more force, the more acceleration. So these are directly proportional. Now, what if here's this car. Let's draw the car again. And here's a force, we'll call this F1. But what if there's a force like this? F2, going the other way, resisting it. Maybe this is wind resistance or something. Well, this force is trying to change the motion to the right. And this force is trying to change the motion to the left. Well, let's say F1 is a little bit bigger than F2. What are we going to do? We're going to add these forces together as vectors to figure out what the net force is. The net force, if you got a lot of forces acting on an object, it's the net force, the force that's left over, that causes an object to accelerate. And so the way we're going to say that is this. I'm going to sum all the forces acting on the object. You've seen this before, right? The symbol, it means to add up. We're going to add all the forces acting on the object. When I get that, that will be equal to the net force. And the net force causes the object to accelerate. And the force and acceleration, the net force and the acceleration will be in the same direction. And the amount of acceleration I get depends on the mass. The greater the mass, the less acceleration I'll get. And this has been empirically derived. It works every time we use it. It is a law of nature. It is a fact. Okay? So there is no act of Congress that can violate this. There's no presidential edict or this is it. By the way, when we say a law of nature, it doesn't mean that like a bunch of scientists got together and thought, well, here's a good idea, we should make this the law. No. It's a law because we never see it violated in nature. It's always true. Okay. And this is, in fact, Newton's second law. And it is, we could write it out in words, but but this is way better. The net force on an object will cause an object to accelerate. The direction of the force and acceleration will be the same, and the amount of acceleration is inversely proportional to the mass. Okay. Now, this way of describing force gives us a way of measuring force. Gives us a way of measuring force. We can say that mass is in kilograms, and we're just going to use the metric system here, and the acceleration is measured in meters per second every second, or meters per second squared if you prefer. Now this is awkward to write every time. I don't want to write this down every time I write down a force. So we have an abbreviation for this collection of, these are fundamental units. This M stands for meters. That's a fundamental unit of measuring length. Time, fundamental unit of measuring time, seconds. You can't break it down. Fundamental unit of mass is kilograms. But these products and quotients of these units, we have a name for it. It is a Newton. If you do something great in science, you just might get a unit of measure named after you. I'm still working on it. So, and we abbreviate with the letter N. So let's say this is 50 newtons, and this is 30 newtons. And let's say this car has a mass of 100 kilograms. Maybe it's a toy car or a go-kart or something. Now I can figure out what the acceleration is on this object. Let's, for now, ignore gravity and friction, and normal forces and friction, anything in the vertical direction. We're just going to stick with the horizontal direction. All right, I'm going to sum these forces together, but I have to add them as vectors. So let's add them as vectors. I got 50 newtons this way. I've got 30 newtons in the opposite direction. So I hook them up head to tail. So that's going to be obviously 20 newtons. So my net force is equal to 20 newtons to the right. I'll just say to the right. And that's going to be equal to MA. Well, what is the mass? Oh, let's say, pretend like it's 100 kilograms. And now we can solve for the acceleration. Take the acceleration will be the 20 newtons divided by the 100 kilograms. And you get 0.2. And notice that if you expand the units, you have kilograms, meters per second squared here, the kilograms will cancel that kilogram, leaving the units of acceleration. And you should always say to the right. Magnitude and direction. Okay. So that is, now we're going to get much fancier than this, right? We're going to do force vectors in 3 dimensions or 2 dimensions and get all crazy and figure it out. Now, how much is a Newton? Well, here I have a Newton, 1 Newton. And why? Because gravity pulls this down. Gravity pulls this little foam rubber apple down with 1 Newton of force. Now, 1 kilogram of mass, where's it? Oh, there it is. There's the 1 kilogram. 1 kilogram of mass is pulled down by gravity with 9.8 newtons of force, almost 10 newtons. Okay, so let's talk about gravity for a minute. And talk about the difference between gravity and weight and mass. So let's do that real quick. Weight and mass. So if I hold this thing above the ground, okay, and so here I'm holding it, so I got to pull up on it. Why? Because gravity's pulling down on it. But if I let go of it, there's only one force acting on it. So let's draw that force. This is the force of gravity. Now, what we just said is that if you have a single force acting on an object, that's the net force, and that net force will cause the object to accelerate. But we already said what the acceleration is if you drop something. And what is that force? Or I'm sorry, that acceleration is 9.8. So the acceleration is 9.8 meters per second squared, and that's straight down. So I could say, well, the force of gravity on this 1 kilogram mass is equal to its mass, which is 1 kilogram, times its acceleration, which is 9.8 meters per second squared. And so I can say, though, the force of gravity is going to be 9.8 newtons. So when you feel this in your hand, it's gravity's pulling down with 9.8 newtons. And it gives you a feeling for how much force that is. Now you're used to dealing with pounds in terms of weight. 1 pound equals 4.45 newtons. So a newton is smaller than a pound. And pounds measure, usually we think of pounds as being force of gravity. The weight of something is in pounds. So here's this weighs 1 newton, and it's not very heavy. It's pretty light stuff. So I'm going to pass this around the class. Here you go. So just feel it. Go and just feel it and just go, ooh, 1 newton.
I thought that was the kilogram.
Yeah, I know, me too.
I am not going to throw a kilogram at you. Well, some of you, maybe. But.
No, I thought you were going to pass it around, then I saw you throw it.
Well, actually, yeah, let's pass this around. That's 1 kilogram of, oh, wait, I need it. I need it. Give me it. Okay. Now I want to show you something. Okay. Weight is the force of gravity. And we're going to study the force of gravity in detail later on. But you all know about the force of gravity. You've all dropped something on your foot. You've all had to carry heavy things. You know, there's this downward pull on everything. But weight is not the same thing as mass. And here's how you tell. Look, if I'm holding this thing. If I took this thing to the moon and held it in my hand like this, it would weigh much, much less. It would weigh 1/6 as much. Okay? Because the moon has less gravity than the Earth. The moon's gravitational field is weaker. Pay attention, please. But if I throw this thing, watch what I'm going to do here. I'm going to oscillate this thing back and forth. Okay? Now, okay, look. If I take this eraser doesn't have very much mass. And so if I want to, shake it like this, super easy to do. Oh, it's really easy. I don't even notice it because it has so little mass. Now, if I took this thing to the moon, feel the same way if I did this. If I took this thing to the International Space Station, I'm in free fall. I don't even feel gravity anymore. I would do this, it'd feel the same. Now, if I held it like this, I wouldn't feel the weight at all. It would just drift off my hand. But if I do this, and I'm going to try and shake this, this is really hard to move. It's really hard to change its motion because it's got so much mass. All right. So that's not going to change on the moon. If I hold this thing on the moon, it'll feel a lot lighter. But if I grab it and try to shake it sideways to gravity, it's going to feel exactly the same. The mass doesn't change. You go to the moon. Okay. Now, if I were to throw this at Patrick's head, okay, I would never do that, Patrick. But I guess a guy can dream. All right. Look, if it's going to hurt. It's going to hurt. Even if you're on the moon, you might say, but this thing's so much lighter. Yeah, it's lighter, but it's still got mass, the same amount of mass. And you still have to change the velocity when it impacts his head, all right? And it's still going to hurt. If I threw this thing as hard as I could on the International Space Station, I'd probably kill the crew. and myself. Why? Because I'd probably punch a hole in the wall with this thing. Well, probably not on the International Space Station. But this thing has still got lots and lots and lots of the same amount of mass. Mass doesn't change with gravity. So just remember that. Mass is a measure of inertia and how much stuff it has. Weight is the pull of gravity. You go to the moon, you've lost weight, but you haven't lost any mass. Yes?
So like shake weights are the way to go for astronauts?
Shake weights?
Yeah, you know, like the things you go like
Oh, yeah. I guess so. That would look funny.
Oh, yeah.
Wait out there, I'm recording a lecture. Come back. All right, so that's really important. The way we write the force. Now the book does this. They use weight like this for the weight. I don't do that very often. I just put the force of gravity. That's how I describe it. Just from regular physics and stuff. It's just in college. That's what we did it. I don't know why the book does this. I always like to say it's a force, and here's what kind of force it is. Okay, F means force, and then this is the kind of force it is. All right. But you can, if you use this and use it properly, I don't care. Do read the book. The book talks a lot about it. Okay, finally, let's talk about Newton's third law. Which is the law of interaction. Okay, I remember studying the physics that you're studying when I was a freshman at Cal Poly. And I'm not afraid to admit that I got stuck on a lot of these problems. And I kind of had a bad temper. And one time I got mad and I lived in the dorms at Yosemite Hall. Yosemite Hall at Cal Poly is made out of concrete. And when I punched the wall in frustration, I got a really great, authentic education of the law of interaction. Because when I punched the wall punched me back. And the wall didn't notice it, but I had like a bruised knuckle and really a damaged ego as well. Like, God, that was the stupidest thing I've ever done. Well, it's at least on the list. So, and I'll say this. For every force on one object, there must exist an equal but opposite force on another object. Okay. 100 years ago, the three major sports were baseball, horse racing, and boxing. There was football and basketball were years away from being considered spectator sports. And boxing was probably by far the biggest. The first professional athletes were horse racers and boxers. Because what happens when there's a fight on the school ground out here? What happens? Everybody wants to see the fight. You think the teachers are running to the fight to break it up, but you notice there's a little hesitation before they dive in. We all want to see the fight. All right? People love a good fight. All right. So, and people notice that, right? So, let's say two guys were were ready to hate each other, and they said, we don't want you to murder each other, but we're going to let you get it out of your system. We're going to set up a controlled fight and have rules so nobody will die. So they would do this, and then people would show up to watch, and then people started making bets. And then bookies got involved. Wherever there's gambling, there's going to be a bookie who's going to make a little bit of money on the transaction and knows the odds, and And so they said, shoot, why don't we hire these guys to fight each other? So they started arranging professional fights. So if you were really good at fighting, they would pay you to come, and you'd fight these people, and people would come and they'd pay money, and Now, if you're a fighter, those early fights, they were actually in some ways safer than they are today, because if here's here's somebody's head. Let me just draw somebody's head. And here's somebody's fist. Yes, you have to draw this fist. I'm not very good at fists. Little tiny baby fist. All right. Now, if you hit somebody in the head, you're going to lose with your bare hand. You might, you take your fist and you punch somebody in the head, bam. Okay, the skull is the hardest, strongest set of bones in the body. It's protecting the brain. And your hand are these skinny little fragile bones. And so when a boxer would hit somebody in the head, they would apply a force, the force of their fist on the guy's head, but the head applied an equal and opposite force. This is the force of the head on the fist. Should be and they are in opposite directions. So when a boxer would hit somebody in the skull, it would, if they did it too hard, they'd give the guy a good knock, a real knot on his head and a bruise, but it would break the bones of their fist. And so what they would do is that it was almost all body blows and slaps. They would slap each other in the face, and they would punch each other in the body, and they would go 20, 30 rounds, and there really wasn't a knockout. They would collapse from exhaustion. But then they started, if a boxer broke their hand, their career was over. Or it was over for a long time, because the bone quite often wouldn't heal right, and they were done. So they started protecting their hands. And so one of the things they could do would be to wrap it with cloth or something, right? You get a cloth, if you get a cloth like this, and you grip it like this, now your fist is more solid, and it's going to absorb some of the impact, and your hand is protected. But you want to keep your knuckles protected too. So you stuff this into a glove to protect your skin, and then you start putting padding on that to protect your hand more, and then all of a sudden you got one of these things, a boxing glove. It's the worst thing that ever happened, because now if you put this thing on, you can hit with your fist as hard as you can, and it won't break your hand. And now you had real knockouts. And the way a boxing match would end was you would hit somebody in the head so hard that it would bruise and damage their brain, and they would collapse. There'd be a knockout. They'd have a concussion. And instead of allowing them weeks to recover from a concussion, as we force football players and so on to do now, they would just, the next night, they would do their next battle, and their next fight, and their next fight, and hundreds of fights. And these guys would end up getting what we call punch drunk. And basically it was brain damage. They could hardly talk. They would just destroy people. So actually, in a lot of ways, bare-fisted boxing is safer. You get more, gouges and so on. But it's all because of this law of interaction. If an object applies a force to this object applies an equal and opposite force to the other object. And the way we do that is we say, okay, the force of the fist on the head is equal but opposite to the force of the head on the fist. See this negative sign? Now, what happens if I add these two forces together? So the force of the fist on the head plus, just add this to both sides, plus the force of the head on the fist is equal to 0. In other words, this force and this force cancel each other out. Now you still feel them, but they cancel each other out. And this is the law of interaction. It's always true. Things don't even have to be in contact. Like if you have the Earth and the moon. Okay, the Earth pulls on the moon with the force of gravity. But the moon pulls on the Earth with an equal and opposite force. And it does affect the motion of the Earth. The Earth doesn't go in a perfect circle around the sun. It wobbles around the sun. As the moon goes around it, it makes it wobble. That's why we have tides and so on. But the Earth, and so these are non-contact forces, the force of gravity, force at a distance, weird stuff. But that's what's going on. And this idea of equal and opposite force is allowed to do the last thing we're going to talk about today. I know this is one of the longer lectures of the whole year, so sorry. We can draw an interaction diagram. So let's say we'll start with a very simple one. Here's the ground, or the floor. Here's a big crate or a table or something like this. And here's my little we'll make it more fun. Here's my coffee mug. So we're going to draw a free body diagram of my lovely rocket scientist coffee mug. Here's a coffee mug. So let's identify my system. I have a system of different objects here. Here is my system. What's in this system? We have a cup. We have a table. We have the ground. And we have the earth. And they're all applying forces. So what I can do is I can draw an interaction diagram. And these get kind of messy, so prepare yourselves. What does the earth do to the cup? Pulls down with the force of gravity. Oops. So I'm going to say this is the force of the earth on the cup. But what does the cup do? Well, here's the earth down here. This is the force of the cup on the earth. Yes, the cup pulls up on the earth. How come we don't see the earth flying up towards the cup? Because the cup weighs about half a kilogram, and the earth weighs 6 trillion kilograms. 6 trillion kilograms. Yeah, that's a lot, in case you're wondering. Now, so here is a force pair. This is a force pair in my system. This force and this force is a force pair. And you can tell a force pair because the subscripts are switched. Now the table. Well, the table pushes up on the cup. So this is the force of the table on the cup. But what does the cup do? This is the force of the cup on the table. So you have a system of objects that are applying forces to each other, and for every force on one object, there exists an equal and opposite force on the other object. We can draw that in an interaction diagram. This is showing the interaction between these objects. And of course, we have the force of the ground on the table. This is the force of the ground on the table. We have the force of the table on the ground. We've got the force of the earth on the table. We've got the force of the table on the earth. Then we have the force of the ground on the table. Oh wait, ground, table, table, ground. Earth. Oh, yeah, I think I got them all now, huh? It's a mess, isn't it? It's a mess. But this is an interaction diagram. And you're showing all the force pairs. Now, let's just draw a picture of the cup. So this right here is called an interaction diagram. Now I'm going to draw what really is important, the free body diagram. The free body diagram is when you choose an object of interest, like the cup or the table. You choose an object of interest and you show all the forces acting on it by outside agents. So I could choose the cup, free body diagram of the cup. So I would do this. Draw my little cup. Force of the earth on the cup, and I can put earth on cup if I want, or I can change the subscript to the force of gravity. Then I have the force of the table on the cup, and we don't really usually call it the force of the table on the cup. You can, and it will be 100% on a test or whatever. Table on cup is fine, but I'm saying it's a normal force. F sub n for normal force. We'll talk about normal forces. We'll define it a little better later on. But this is the force of the table on the cup. This is the force of the earth on the cup. But we're only showing the forces on the cup. We're not showing the forces of the cup on the other things. That's a big idea right there. I'm going to draw a free body diagram of the table. I won't draw a free body diagram of the ground or the earth, just the table. So here's the table. I'll make it a little smaller. Sometimes we just draw these as dots because we don't really care about their extent. We just want to look at the object. Okay, well, what do we got? We got the force of the cup on the cup on the table. We got the force of the earth on the table, force of gravity if you want to call it. Oops, tilted, sorry. And then we have the force of the ground on the table. Table, table, table. I'm only showing the forces acting on the table. Now what do these forces have to add up to? 0, right? So what does that tell me? Well, the weight of the table plus this force of the cup on the table, which is really the weight of the cup, has to be canceled out by the force of the ground pushing up on the table. Okay? So that lets us start making predictions about what things should be. One more free body diagram. I can take this whole system, or I can take this cup and table, and I can combine it into one free body diagram. So you can do that. And what happens when you do that is this table on cup and cup on table become internal to the free body diagram. And so they cancel out. So let me get another sheet of paper and draw that. So here's my cup, and here's my table. Now, if I say, okay, I've got the force of the earth on the cup, earth on cup, force of earth on table, and here's the force of the ground on the table. But then you might say, well, what about the cup and the table? Well, if you put the force of the table on the cup and the force of the cup on the table, notice they're equal and opposite, so we do not include those in our free body diagram because they are internal. Those are called internal forces. Interactions among objects that are part of my free body diagram, they cancel out anyway. This is a big deal. So this would be my free body diagram. I have the ground pushing up on the table, the force of the earth on the cup, and the force of the earth on the table. The total weight, actually, when you add these, that's the total weight of your system, and this is the ground pushing up on it to support that weight. Okay. Now this is one of the longest lectures of the year. Actually, and I'm sorry it's so long, but these are really, really important ideas. The most important ideas you'll get this year. And so let's just very, very briefly review what we talked about here. We talked about Newton's first law. We said that objects don't change the way they're moving unless you force them to. We call that inertia. Objects can be made to accelerate by things called forces. The amount of the force and acceleration will be in the same direction, but the amount of acceleration you get depends on the mass. The greater the mass, the less the acceleration. If you double the force, you'll double the acceleration. But for the same force, if you double the mass, you'll cut the acceleration in half. You have to add all the forces acting on an object to get the net force, and it's the net force that causes the acceleration. Don't confuse gravity and weight with mass. Weight and mass are very, very different. Weight is the force of gravity pulling an object down. Mass is a measure of inertia, your resistance to acceleration, or the amount of stuff you have. That doesn't change if you go to a different planet. Your mass doesn't change. Your weight will. And then interaction. For every force on one object, there will exist an equal but opposite force on another object. You can use that to draw an interaction diagram, and you can use the interaction diagram to draw a free body diagram. The free body diagram is the most important skill that you can develop here. Let me tell you something. I have students, that have gone through regular physics and gone to college, and AP physics and gone to college, and they always come back and say, if they're going to be engineering majors, they always come back and say, thank you for making us learn how to draw free body diagrams, because I'm the only one here who understands how to do it. It is a skill. It's a way of looking at the world. It's a mindset and a skill. Being able to look at an object, look at all the interactions it's having within a system, and then taking those forces, figuring out what the net force is, and then if you know the net force, you can figure out the acceleration, and you can figure out how this object is going to move under those forces. And that is the very fundamentals of designing a machine and doing mechanical engineering. Or if you're doing civil engineering, a lot of times there's not a lot of acceleration in civil engineering. You don't want a bridge to accelerate. You want it to be in equilibrium. Equilibrium is when all the forces cancel out. So you have zero net force, so you have zero acceleration. But even that requires a free body diagram to figure out what the forces are going to be, so that you can design things and make them strong enough to withstand the forces that will apply. So I will say this, look, chapter 5, the most important chapter of the year. You guys are starting to get busy and you're starting to get weary. It's the 5th week of school and you're starting to get sick of this. This is when the novelty of the school year wears off. I am telling you this, do your best work for chapter 5. Stay caught up, read the book, listen to the lectures, think very hard, do the homework on time. If you do that through this, then if you get tired and you want to procrastinate a little bit, you can probably recover. But if you get this stuff, the whole rest of the year is easier. That is all.